Yeah, I'm going to just, within a few minutes, indicate to you the fact that different bootstrap methods actually exist. Bootstrap, and I should emphasize, different bootstrap confidence interval methods exists. And I'm going to show you one more thing. I'm going to indicate to you how such simulation methods that I've been giving to you in this course can actually be used to investigate how good different such methods actually are. So that is the nice thing about simulation, that you can use it not only to produce results, you can use it to actually in a way go check such results that you produce. So that is a kind of strength of simulation-based methodology. And so what I taught you in this course as the basic bootstrap method, that is what is known as the percentile method, where you simply take the observed bootstrap distribution and take the quantiles in the ends and use that to produce, say, confidence intervals and maybe sometimes also hypothesis tests. That's the basic method. There is another method. Actually, there are quite a few, but here are some of the main ones. There is something which is called sometimes bootstrap T method. In the bootstrap T, you do something slightly different than the simple percentile. What you would do in constructing a confidence interval for bootstrap T, you would go for taking the estimate of whatever you compute. Now we call it theta. It could just be the average, but now let's use the general phrase or the general term theta hat. You would take the 1 minus alpha of something, and I call it T star, of some distribution, times the bootstrap standard error. I write it like this. So, and then we take the two quantiles of this, the alpha and the 1 minus alpha quantile, times, so in a way we construct the confidence band like a T-based confidence interval. However, these ones are coming typically as bootstrap standard errors. Like, I mean, following the same principle as the class basic principle. And we're not quite done, because we are not actually using the T distribution. We are getting those T's from something else, actually. Not from the T, but from the simulated sort of T-type, T-kind of distribution. So we don't use the T. We actually, again, simulate within the simulation, actually. So it is coming from something. If we look at the Beath bootstrap sample from up here, from the you could say the outer bootstrap, we would go ahead and compute this one based on the Beath bootstrap minus the original one, and then we would estimate actually kind of a standard error within the Beath bootstrap. That is, within the single bootstrap, based on that bootstrap distribution, we would do another bootstrap. So we sort of bootstrap standard error, and I emphasize from the Beath bootstrap sample. So it's bootstrap within the bootstrap, actually. It becomes more computationally challenging, but that would be it's in a way trying to correct for the fact that the distribution is not always fully symmetric and nicely, even though we kind of bootstrap. Now, that was the second method that I will touch on, and then the third method I won't even write up. I just want to tell you that it exists, something which is called the bias corrected and accelerated so-called bootstrap. a way, and I'm just going to, it's a way to sort of correct for bias and skewness in a way in the bootstrap distribution. So you could actually set up a way to try to, a bit similar to the idea from up here, but still in a different way, trying to acknowledge the fact that the bootstrap distribution itself is a bit skewed and biased, and use that to construct a bit more, in a bit more complex way, a confidence interval for whatever you want to compute. Now, let us try. I'm going to show to you a small simulation study I've done in trying to, just to see how good are these three methods actually for the very basic setting that we could be interested in, namely how to compute the mean of a single sample. How good are these three methods? And I'm going to show the result of this, and I'm going to indicate to you by looking in R how such results can be produced. Let's have a look. I am going, first of all, to study 4 different situations to make my comparisons of those 3 different bootstrapping principles. I am going to look at the classical case where the data actually is normally distributed. Then I'm going to look at data that is truly uniformly distributed. So the idea is I'm going to try this many times now in different situations and see how does it actually work. I'm going to look at this odd distribution, which is the chi-square distribution, another, you could say, non-normal distribution, and finally, I'm going to look at such a weird thing here that actually occurs a lot in practice, that you could have settings in which data follows an odd distribution like this with maybe a lot of zeros, and 50% of the time on average it could be a 0, and in the remaining time maybe it's log normal, for instance. That's the 4 distributions that I will look at. Now, the results as they come at the end, before I dig into the R, looks like this. Let me try to explain what these results are showing us. First of all, I have one box, one plot for each of the 4 distributions. So what have I done? Let's start with the normal distribution. I have, for instance, if we take, and then I have 4 different settings. I have n equal 25, n equal 16, n equal 9, and n equal 4. Let's take the n equal 25 setting here. Now I have many times simulated normally distributed data with a mean of 0. That is, I know the mean. So I do that many times, normal samples of 25, and then I compute on each of those, I compute the confidence interval. I compute the confidence interval by 4 different methods each time. I compute it by the standard t method, so t-test based or t-statistic based, no simulation or anything, just t-based confidence interval. And then I use the 3 different bootstrap methods that I have talked about now, the percentile one, the standard one in our course, and then the 2 extra ones, the BCA, bias and accelerated, and the boot T. Now, if we then look, and then what I'm showing you in this diagram, you can see I call it coverage probabilities. That is when I many times compute the confidence interval for a mean. And since I simulate the data, I know what the mean is, and I simulate with 0 mean in this case. So I simply count how often do the confidence interval include the true value. Since I have set the true value, I can count how often the confidence intervals includes the true value. And for a confidence interval to be a good method, it should include the true value, exactly the amount of time which is expressed by the alpha level. So when I construct 95% confidence intervals, I want this method in exactly 95% of the time, not more, not less, but in 95% of the time. For this to be a good confidence interval method, it should include the true value. What we see, for instance, in the first plot, where I applied on data that are truly normally distributed, we see the fact that the standard t works fine, right? The red one, as it should, because it's based on that assumption. So the standard t is exactly on the coverage probability of 95%, because I construct 95% confidence intervals. The standard t, but also the boot t seems to be the only one, actually, among the bootstrap methods, that when we go down to N16, N9, and even a sort of ridiculously small sample of only 4, then only the bootstrap t provide valid results like the t distribution itself. The other bootstrap methods are actually a bit pushed here and do not even work nicely here. Not so nice, but that's a fact. Now, maybe to the more interesting things, how do these methods perform when distributions are not normal? The general picture is they perform quite differently depending on what type of non-normality is going on. It's rather complex, but that's how it is in a sort of such more research-based investigations. What we see, for instance, for the chi-square distribution is that the standard t, which is the red one, really breaks down. It has a completely wrong coverage probability, but we also see that it's really, again, the bootstrap t, the light, whatever green, blue thing there, is the one performing the best. And the other bootstrap methods are actually, funny enough, performing even worse than the t. Here, they are even further away than the t from the true coverage probability. However, the bootstrap t seems to be a pretty good method, which I believe it is, as an alternative to the standard percentile method. However, we do see a problem with the bootstrap t thing in the mixture. The mixture distribution was the thing with, this was the mixture. In this case, the bootstrap t seems to be too liberal. It includes the true value too often. So it's not even a good method. And even for the mixture distribution, I would still claim maybe the standard t here to be the winner among these methods. Now, this is not 100% to be believed in a way, because there are actually many different ways we can do some of these bootstrap methods. So it can be rather complex. Let me just spend a few minutes, not giving you details, but showing you how such methodology, how this can be done in R to actually investigate. And I just want to give you a bit of sketch, because it's not easy to go lecturing on software code. The thing is, I would go to use the Bootstrap library. I would tell, generally speaking, that I'm interested in the mean. I would need, just as a detail here, I would need to set up a function to simulate this funny mixture distribution, since that's, at least I didn't find such a direct procedure in R to give me that. So basically, without details, I use a binomial to simulate whether it's going to be a 0 or either it's a 0 or it's a random log normal. So that's the mixture distribution I've put into my own function here. Then I use, and that's maybe the interesting part, I use the fact that as a part of the Bootstrap package, I can do either simple Bootstrap, as I've taught you in this course, where I look directly on the quantiles of the Bootstrap distribution, or I can use the accelerated and bias corrected, which is a function built into R. I can directly, sorry, this is my own function, but I apply that this is my own function including the results. But there is an R function, which is the B canon here, that exactly uses the BCA, Bootstrap confidence intervals, and there is a boot T function that gives you the Bootstrap T confidence interval. So it's very easy for us to go investigate how these things apply. Well, for the boot T, you do have to set an option on the number of Bootstrap sample in the inner loops, this Bootstrap within Bootstrap, and I've set that rather low. Maybe you could play around with setting that at a higher level, but this is just for this illustration. Then I go on, I shouldn't do the details for you, but I go on, and for each of these n's, 4, 9, 16, 25, I do my, just as an indication here, I would do, for instance, my normal distribution simulation. I will go ahead and do the classical t-testing here. Basically, that's what I do here, that I construct the lower and upper confidence limits by the t-distribution, and then I count, this is the key point of simulation, I count how often do I include the true value in this confidence interval. Then I go on, still for the normal, and do the simple Bootstrap confidence intervals, and I count how often does it succeed to, how often does it include the correct value. I do the BCA Bootstrap, and I count. I do the Bootstrap T Bootstrap, and I count, and I collect all this information, all the probabilities for the plot that I just showed you a second ago. Then I go on, then I do the uniform simulation. I apply standard T, and I count, and so on and so on. I apply the 3 different Bootstrap counting, and I do it throughout for the 4 different distributions, and finally I plot the results. So these, of course, this is impossible to follow the R thing. I just wanted to share with you how this can be done. Not only doing the different bootstrappings can be done by functions in R, but also setting up simulation studies that can reveal to us which methods might be good in various situations. Plot like this. That is used a lot in research in many ways to investigate different methods by such simulation. So that was my idea of this additional math lecture here. Thank you.